Hey, this is day 23rd of the 30-day Leetcode challenge. Let's look at today's challenge. Hit the like button, hit the subscribe button. Now I do this live, so if it takes a little bit longer, or a little bit slower, well, it is live. So let's take a look. Given a range of bitwise n of numbers range, given a range n where m and n is between 0 and 2 to the 31st minus 1, return the bitwise n of all numbers in this range inclusive. Huh, that is interesting. Okay. Huh. I mean, I think this requires some thinking, obviously. Um, so my first thought when I see this problem is that, well, for bitwise n, you're always going to be dominated by the 0, right? So, and what does that mean on a bit? That means that yeah, and well, the other obvious thing maybe is that because m and n is goes up to 2 to the 31st minus 1, well, you can't just do a for loop. So it's not that easy because if you know because you're going to run into time limit issues if you're going to try to do that with a bitwise n for all the numbers. But again, we can kind of we do. So the first thing that I'm thinking about is that, well, we have some properties that we know, and then try to figure out a way. What I'm trying to do right now, as I'm talking through it, is trying to figure out a way to use that property to build a solution of that property, um, and yeah, the property that I'm noticing, obviously, with bitwise n, as we already mentioned, is that it's going to be dominated by 0 bits, right? That means if there are any numbers within that range that has a 0 bit, then 0 in that range, then it's going to be false, or it's going to be 0 for that bit. And I don't really have the solution yet, but my little sketch of an outline of a problem is like, okay, it's something like, okay, maybe something like bit by bit, from the 1 bit, from the 2 bit, from the 4 bit, from the 8 bit, and so forth, and then kind of see whether, like, okay, uh, for example, let's start with the odd numbers because one is an easy way to put it. For given m to n, is there does it exist an even number, right? And what does that mean? That means if there's an even number, that means on the rightmost bit, it is 0, right? Because if there's an even number, anything and that even number is going to be a 0 number. And then from that, we do it bit by bit, and then you could kind of do it recursively, or I mean, I'm thinking of it recursively, but you could do it with while loop, obviously, because there's nothing that crazy about it. But basically, you do it bit by bit and calculate. Okay, now now that we saw that there was an even number, now we divide all the numbers by 2. Well, what happens when you shift everything by or divide everything by 2? Well, your 1 will go away because we already took care of it. 2 becomes 1, 4 becomes 2, 8 becomes 4, right? So still dot dot dot. And now you can ask the same question again. Given m to n, does it exist? This is a very poor grammatic question. That's why I laughed a little bit. But you still get the point, which is that, well, now, is there still a even number? If there is, then it becomes 0 again. So that's kind of the sketch of the algorithm that I've been thinking about just now. And that's what I'm going to try to implement and then play around with that idea. Okay, let's go. So how would we start? So let's start by, well, let's just say we have an answer is equal to 0, doesn't, we return it. And then now let's just call it an offset, which is 0. And this is just to keep track of which bit we're on so that when we put it into the answer, it's a little bit easier because if you shift and then you have to reverse and stuff like this. But okay. But now we have to check if it's the while my guess is that if while n is not equal to n, because or or maybe equivalently perhaps, while m is greater than 0 or n is greater than 0, right? So now we have to answer the question, given m to n, is there an even number between m and n inclusively, right? I think it's inclusive, yeah. Yeah. Okay. Yeah, and then now how do we figure out if there's a even number? Well, there is a even number if the delta is more than, well, basically if m is not n, then it is not, then there's a even number in between, right? Just by, because if m is equal to n, then you get, a bit. But other than that, like given 5, 6, 7, there's a even number and so forth. So actually, maybe that actually becomes interesting. And this is something that, like, if you see me thinking through it now, this is just coming to me. So I'm just thinking it through very slowly, one by one step at a time, one piece of information at a time. So if m is equal to n, then let's OR the 1 to offset, and then otherwise offset plus 1, and then also m left shift by 1. Oh, the other way, right shift by 1 and right shift by 1. And actually, maybe I'll just, to make it slightly clear, we divided by 2 on both of them, as we said, as we shift to the right. And here, maybe it's a little bit more magically, but it's just, you could think of it as 2 to the power of the offset. And then we add it to the answer. That's pretty much it. Maybe that's good enough. Let's give it a try with our inputs. So that worked for that one, 0, 1. What's a good number? 0, and well, we could try the big number, though in this case, we kind of know that this will take only log n, where n is the number of bits. N is, or m, log m, sorry. How come I didn't get an expected answer from this one? That seems like it'll be in the input. Does that mess up their answer? But yeah, we get something like, I don't even know what's a great answer for this one, like 6 and 8 maybe? Also not getting an answer, but we give 6 and 6. Oops. I don't know why this is not, does that crash the system? Is 0 not in the input? No, 0 is in the input. That's really weird. But, okay. But now we're just testing, waiting for this test. Okay, so we do get an answer that's wrong. I mean, so our algorithm, or at least in my mind, our algorithm is right. It's just that we clearly got a wrong answer on this. Oh, there's one more condition I think that I missed. That's why. But that's why you check these things, which is that if m is equal to n and m is an odd number, I think maybe that's maybe if you're viewing at home, maybe that's obvious while you're watching it. But now it makes more sense, right? Oops. Whoops. It's odd number. I said the right thing, but I typed the wrong thing. But that's why you run system tests and stuff like this, right? And the reason why this is if it's a even number, then that last bit is already even. Then obviously there's a even number in between. So the only way there's no even number between m and n inclusively is if they're equal and they're odd. Okay. So I mean, now maybe we could do something like 12, 6 and 12. Kind of multiply by 2, though maybe that doesn't make sense because yeah, well, there's too much. So now maybe 6 and 6 times 8, or 6 plus 8, so 6 and 14. So in theory, that should still be 6, maybe? No, that's too many numbers. I don't know. I don't know what's like a good edge case that isn't. I'm trying to think about an edge case that comes up where like it would, because you can put as much examples, like I could put like obviously like 100, 100, and that'll give me the right answer. Maybe 100, 101 actually. But but like you want to test a good test case is a test case that tests your assumption and gives you an answer that would be wrong, right? Like especially when you know the expect or when they give you the expected answer, uh, where where things that proves you right just gives you a little bit more confidence. But I think I'm okay now. Let's give it a go and then see what case I miss maybe. Yeah, okay, accepted. Cool. Uh, whew. So this is definitely a tricky problem because it really forces you to. I mean, it's a very um, like it's a, I would classify this as an ad hoc problem in the sense that like it's one off. I don't know the techniques that you learn from this problem. You may generalize in a easier way. Um, Except for that, I think one tip of the advice I would say for these kind of bitwise problems is that try to look at each bit one bit at a time, because well, clearly for this problem, if you do something over 2 billion, it's going to be too slow. And now we do log of 2 billion, which is like 32 or 31, depending on how you want to count. So which is good enough. So you have to look at each digit by digit, and from that, I would try to figure out in this case whether there's independence between the different digits, like whether, you know, answering the answer for one digit change the answer to the other digit. And kind of when you see my solution, I built those digits one bit at a time, um, and they don't really rely on each other, right? Like I just do an OR for the offset. So yeah, but it's a very tricky problem. I don't know how you would go about practicing it. To be honest, I'm a little other than practicing it. It is a little bit ad hoc and a little bit one-off. That's what I would say because I don't like if you rewatch the video, like every step of the way was very like given try to find something that you know that is true and then try to build a little bit on top, and so forth. And that's how I kind of came up with this algorithm. And even then, I was a little bit wrong, or at least like I missed a little bit. So, but once you're on the right track, you can kind of build on top of it. So in terms of complexity, this is obviously all of one space. We don't really use any extra space. And as we talked about it, is all of log n, where n is the bigger number. But of course, technically n, in the general sense, n would be the input size. And this is linear because your input size is actually the number, which is a 32-bit number. So it's all of 32 kind of. I mean, I'm hand wavy a little bit on the explanation, so it's all of log n or of n depending on what your n is. But if your n is input size, then it's linear. And yeah, as an interviewer, I don't know if I like this problem. As an interviewee, I don't know if I like this problem, though it is kind of interesting and cute. I mean, it's a fun brain teaser. I don't know if it's a good interview problem because I don't know what it demonstrates to me as a like what it demonstrated candidate to me. But it does, maybe some little problem solving skill, but I would like some more scoping on the coding part. The coding is a little bit too trivial once you figure it out. But otherwise, yeah, a good problem or a fun brain teaser. And I guess it's a good practice. I don't know. I would probably, if I had to kind of rank how I would choose my time, I might not practice this problem. I would maybe choose to focus on, getting better at the more fundamental problems like the binary searches and the depth first search and the breadth first search first. But it is what it is. Anyway, that's all I have for today. If you like this one, if you like how I solved it or whatever, hit the like button, hit the subscribe button. Also, how did you do today? Let me know how you did. Did you like this problem? And leave a comment below. All right, thank you.